Welcome, fellow chemists, to part 2 on the nomenclature of alkenes, where we will start with the cis and trans isomers. This video will be quite different from the previous ones, as you will get your chance to name the examples at the end. Not all alkenes can be classified as cis or trans, and this happens when an sp2 carbon has a pair of identical substituents on it. The letter R is a stand-in for that substituent, be it hydrogen, halides, or something else. So on this particular molecule, the carbon on the right has identical substituents, so it cannot be classified as cis or trans. Now, how to go about identifying a molecule that can be classified as cis or trans? We split the molecule along the double bond and look at the position of the parent chain. If the path of the chain is on the same side of the double bond, we classify it as cis. We add the prefix before the name of the molecule. So this one is cis-hex-3-ene. Now I am sure you know what is coming since the chain location has been altered. We still want to split the molecule along the double bond, and when we follow the path of the chain now, we see its position is on opposite sides of the double bond. When this happens, the molecule is classified as trans, and we add that prefix before the entire name of the molecule, trans-hex-3-ene. So, in summary, if the molecule can be classified, and the chain continues on the same side of the double bond, it will be classified as cis. If the chain continues on opposite sides of the double bond, this of course will be classified as trans. Now for the isomers of alkenes named with a different system, the EZ nomenclature system. While cis and trans is useful for simple alkenes, it does have its limitations, so the EZ system is the preferred one. In this case, there are 4 rules that designate priority to groups, and if those groups are on opposite sides, we use the letter E, while Z is used if they are on the same side. The first priority rule applied is the greater the atomic number of the atom, the higher the priority. Let's take these two molecules that are otherwise identical except for the arrangement of the substituents on the double bond. On the first molecule, the carbon on the left is bonded to bromine and hydrogen. The bromine has the higher atomic number, so we give that the priority. Meanwhile, the carbon on the right is bonded to a chlorine and directly to another carbon. Since chlorine has the higher atomic number, we give that the priority. Cutting the molecule in half and boxing the higher priority atoms, we see they are both on the same side, so this is the Z isomer. Meanwhile, the molecule on the right is otherwise identical, so the priorities will be the same. However, the positions of the atoms relative to the double bond have been shifted. So when we split the molecule in half, we see the priority atoms are on opposite sides of the double bond, so this is the E isomer. If the first atoms we check are identical, move on to the next atom to determine priority. As before, the molecules we see are identical except for the arrangement about the double bond. On the first molecule, the left carbon is bonded to bromine and directly to a carbon, which means the bromine gets the priority. The right carbon is bonded to carbon on the top and another carbon on the bottom. So since we have a tie, we must check the next atoms. On the bottom we have an oxygen, and on the top we have a carbon. Since oxygen has a higher atomic number, it gets a priority. Checking the locations reveals the priorities are on the same side, so we have the Z isomer. Now you already know what is coming for this molecule on the right. The leftmost carbon of the double bond bonds directly to bromine and carbon, so the bromine will get the priority. Meanwhile, the carbon on the right side bonds directly to 2 other carbon atoms, so we need to break the tie. Of course, we find the oxygen and the carbon as the next atoms, so the oxygen will get the priority on the right side. When we check their locations, we see they are on opposite sides of the double bond, so we have the E isomer. In case of a double or triple bond, you count it as 2 or 3 bonds to that particular atom. So to break the tie, you have to look at all the bonds from the original. So these two molecules are again identical except for the arrangement of the substituents. We see the carbon on the bottom left is doubly bonded to oxygen with a single bond to hydrogen. The carbon on the top left is only singly bonded to oxygen with 2 bonds to hydrogen. The tie is broken because the bottom carbon is classified as bonding to an additional oxygen, so it gets the priority. There is a similar situation happening on the right side of the molecule. The carbon on the top is considered doubly bonded to a carbon and once to a hydrogen, while the carbon on the bottom is only singly bonded to a carbon and twice to a hydrogen. So the carbon on the top will get the priority. We see they are on opposite sides, so we have the E isomer. When we look at the molecule on the right, the groups still are bonded in the same way to the same atoms. So the group on the bottom left will get the priority because that carbon is bonded twice to an oxygen. When we look on the right side, the same group is going to get the priority, so it's going to have the carbon with the double bond to a carbon because that is considered to be bonded to two carbons. Since these priority groups are on the same side, we have the Z isomer. For the fourth and final rule, we bring in isotopes. The priority will go to the one with the higher mass number. This can be a comparison between any element and its isotopes, but for this example, we'll stick with hydrogen. The heavier isotope of hydrogen in this case is deuterium, but it has the same atomic number, of course, but it will have a higher mass number. The mass number of deuterium is 2, while that of the usual isotope of hydrogen, also known as protium, is 1. So the deuterium gets the priority on the left side. On the right side, since bromine has a higher atomic number compared to chlorine, it gets the priority. The high priority groups are on opposite sides, so we have the E isomer. When we look at the molecule on the right, we are going to find the same priorities for the same elements. Deuterium and hydrogen have the same exact atomic number, but of course deuterium has a higher mass number than the hydrogen. So of course deuterium will get the protium on the left side. When we look at the right side, we still have bromine and chlorine, and bromine has the higher atomic number, so it gets the priority. When we look at the locations of the priority groups though, we see they're on the same side, so that is the Z isomer. Now let's take a look at a few examples and how they are named. I suggest you pause the video and try yourself, but do not be discouraged as there are a couple of things I have not covered in a video yet. We start off with a fairly simple example, so here is your chance to give it a go. So first we need to figure out the isomer. Based on priority, chlorine beats carbon on the left, and carbon will beat hydrogen on the right. So they're on opposite sides, so we have the E isomer. The rest of the name is not too difficult to put together, and we get E, 2-chloro-pent-2-ene. However, eagle-eyed viewers might be asking, what about cis or trans? Well, let's take a look. The chain itself continues on the same side, so we have cis 2-chloro-pent-2-ene. This happens because cis-trans and EZ systems are different and not interchangeable. Now with example 2, give it a go. Following the priority rules in order to determine E or Z is pretty straightforward even on a molecule like this. The priorities, which both end up being bromine atoms, end up on the same side, so we have the Z isomer. Following all the other naming rules that we know, we get the full name Z 1,4-dibromo 3-ethyl hex 3-ene. If you're paying attention, you know you'll need rule 3 in order to determine the isomer, but can you name the whole molecule? So rule 3 is the multiple bonds rule to determine priority. With the double bond taking the priority on the bottom left, and the top taking priority on the right, we are going to have the E isomer. Naming this molecule involves nomenclature with multiple functional groups, a topic for a future video. But in the case of two double bonds, we use the prefix di just like we did for two bromines. The full name is E3-ethyl 4-methyl hepta 1,3-diene. For the final example, try to name the molecule, but I must warn you once again, there is something here I have not yet covered. On the left, we see the isotope deuterium, so it gets priority. And on the right side, the top of the molecule will get the priority. This, of course, is a Z isomer, and most of the name is pretty standard. We get Z 2-methyl but 1-ene, and the new part, a 1 with a D to indicate the presence of deuterium. I'm going to let this run without much of an explanation, but the typical IUPAC preferred method of naming when isotopes are present is being demonstrated now. The letter D for deuterium has been replaced by its nuclear symbol, 2H, and you will soon see how the rest of the name differs from the previous example. However, do you at least understand why the molecule is classified as E as opposed to Z? Another question you might ask is, shouldn't we be wrapping this up about now? And yes, we definitely should. To summarize the isomers, if a carbon in the double bond has identical substituents, it cannot be classified cis or trans. When the carbon chain continues on the same side of the molecule, it is cis, and if it continues on opposite sides, it will be trans. Despite the similarities, the EZ system does not correspond to the cis and trans naming. For E isomers, the high priority groups are on opposite sides, and for Z isomers, they are on the same side. The higher the atomic number, the higher the priority. If the atomic number is the same for the first atoms encountered, move on to the next to break the tie. Multiple bonds count as if the atom is bonded to multiples of that particular atom. Finally, in the case of isotopes, the higher the mass number, the higher the priority. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. For my recommendations this time, it will not be chemistry but astronomy, because I am as fascinated by the wonders of space now as I was when I was younger. Dr. Becky Smethurst will keep you up to date on all the astronomical events you should look for in the night sky, and I find her videos on the history of how astronomers and astrophysicists develop their current understanding incredibly interesting. Over on Deep Sky Videos, you will browse the Messier catalog and also visit some of the coolest telescopes on Earth. You'll find links to their channels and websites in the description. If it is not nighttime or if the sky is clouded over, take a look at some of my previous videos. Please feel free to get in touch with me via email, social media, or if you would like, make a request in the comments.